All right. So we're gonna look at 5.3 Part 2. We're gonna introduce some new scenarios with substitution that we could possibly have. We're gonna look at rational functions. So ones where we could substitute in for the denominator and be left with 1 over u du. And we're also gonna look at exponentials with base e. So for 5.3 Part 1, we looked at these first three scenarios. Integration where we had quantities being raised to an exponent. Ones where we had angles of trig functions, so angles on the inside that were being raised to an exponent, or products going on the inside. Then we also had the scenario where you had trig functions whose derivatives were contained in the integral. So I could go ahead, let one of the trig functions be u, take the derivative, and that other trig function was in there as well. In this video, we're looking at denominators of a rational function, so when we can let those be u, and also where we have an exponent for an exponential function in the form of e to the u, where we have e as our base. So the first time when I made this video, it actually wasn't recording, so I actually have a couple of these already written out, so just talk my way through them. On this page, we're looking at functions in the form 1 over u du. So it's where we can go ahead and let the denominator be u. When we go ahead and integrate that, it's going to be equal to the natural log absolute value u plus c. So looking at number 1, it's the most basic scenario. You look at it, you got dt over t. So if you were to try to integrate that, it would be t to the negative 1. Can't do it. We kind of already talked about this. When you have a setup like this, it's going to be the natural log. But what we can do here is we can go ahead and let u equal t. Take the derivative of it as dt. When I substitute back into my integral, it's the antiderivative or integral of 1 over u du. Going with the natural log absolute value of u plus c. And then we substitute back in. So number 1 is the most basic one. Number 2, we kick it up a little bit. I can't let the numerator be u because if I take the derivative, there's no way we can match it up. So I go ahead and let the denominator be u, x squared minus 5. Take the derivative of that. We're left with 2x dx. I look at it, everything matches up. So I got u and then 2x dx is what we're looking for. That's the derivative I got there. That's what we said du was. So I go ahead and substitute in. It's the antiderivative du over u, which turns into the natural log absolute value of u, plus c. And then that is equal to the natural log of the absolute value, x squared minus 5 plus c. Substituting back in. So still nothing crazy. The fun begins when we get to example 3, and honestly, this isn't even that bad either. We go ahead, let the denominator be u. Okay, so now I got trig functions up top, down below. We're going to let the denominator be u. 3 plus 2 sine theta. Take the derivative of that. It's going to be 2 cosine theta d theta. Now, when I go back to my original integral, I need 4 cosine theta d theta. Right now, in the purple, I only have 2 cosine theta d theta. So to get it to be 4 cosine, I need to go ahead and double each side. So I multiply by 2. So I'm going to have 2 du is equal to 4 cosine theta d theta. To integrate it, I go ahead and throw the 2 out front. I have 2 antiderivative du over u, which turns into 2 natural log absolute value of u plus c. Substitute back in. We're left with 2 natural log absolute value 3 plus 2 sine theta plus c. Okay, for number 4, we get in the habit of just saying, hey, the denominator is u, but remember, the reason we're doing that is because the derivative of the denominator shows up in the numerator. For this one, if I let x be u, derivative of x is just dx. I have this ln x here I can't do anything with. Okay, so I'm going to go ahead and let the numerator, in this case, be u. So u equals the natural log of x. Go ahead and take the derivative. I get du to equal 1 over x dx, which when I look at it, matches up perfectly. I can go ahead, substitute in u du. So from there, we go ahead and integrate. Get u squared over 2 plus c. Substitute back in. And we call it a day. This next example, number 5, is the first one where we actually have to actually do some thinking here. And it's going to follow a pattern, a rule that we could always follow. Or honestly, you could always use sub this if you wanted to. So I have the integral of tan x dx. I can rewrite tangent as sine over cosine. The reason I'm doing that is because tangent of x, when I think of the derivatives of trig functions, there's nothing we can do with it. Okay, nothing matches up. No good, can't do a thing. So I rewrite sine x cosine x. When I do that, I can let the denominator be u. I take the derivative, I get negative sine x. Then I know, okay, if I multiply or divide by a negative, I get it to match up perfectly. I get to be a sine x. So I go ahead and substitute in. We got the antiderivative negative 1 over u du, which is going to be negative ln u plus c. And I get to this point right here. I get negative natural log absolute value cosine x plus c. One thing you want to pay attention here is that properties of logs tell me that the number out front is the same as an exponent. So this also could be written as the natural log absolute value cosine to the negative 1 of x plus c. Not like that. Like this. Or that is also known as the natural log secant x plus c. Either one of those work. And that's where when we come down here, they have these two rules. So when I have the antiderivative of tangent, we could say, hey, it's the negative natural log cosine u plus c. And then if I had cotangent, we could have the opposite. We could say it's equal to the positive natural log sine u plus c. You could also take these out to secant, cosecant if you wanted to. I'm honestly going to leave it alone. So for number 6, if we wanted to, you wouldn't even need to do like u sub on this. You wouldn't need to rewrite it. You could just notice and say, hey, tangent is going to go to negative natural log absolute value cosine 2x plus c. And then we remember when you have a coefficient, so this constant rule for trig function angle still applies. When you have a constant, we have to divide by it. Gets us to that point right there. So it is a rule you could follow. If you wanted to, you could always go back, though, and deal with u sub on this, and you would still get to the same answer, which is perfectly fine. We're going to finish this up by looking at functions of the form e to the u. Okay? So when I have an integral of e to the u, du, it's just going to be e to the u plus c. Done. That's it. So we use substitution for integrals of e raised to anything other than the first degree variable. Constant rule for the trig functions will work for first degree variables with coefficients as well. So you're going to see a pattern with this, and it's super easy. Go ahead and let the exponent be u. We take the derivative. We get 3dx. Okay, so got that right there. Go ahead and solve. Well, not solve, but we got to get it to match up. I just want dx. The way we're going to do that is we're going to take a third from each side. So I'm left with 1/3 du. If I go ahead and write my integral out, it's going to be 1/3 e to the u du. We do the integration. I get 1/3 e to the u plus c, and then we substitute back in. So I'm left with 1/3 e to the 3x, and I'm off the screen. 1/3 e to the 3x plus c. Done. Okay. I'm not going to write all this out. Okay. You should get in the habit of doing this pretty quick. I go ahead and integrate it. It's going to be the same. E to the negative 5x plus c. Let me divide by negative 5. Do this one right here. It's going to be e to the 9x over 9 plus c. Done. If you wanted to, you could also rewrite these. It doesn't really matter. But you could rewrite these as negative 1/5 e to the negative 5x plus c. And you could also write this one as 1/9 e to the 9x plus c as well. Those also work out. Last one we're going to look at, and honestly it's probably the most important one, is where the trig ratio or the trig function is in the exponent. This is really like we got to do a little bit of thinking on this. You go ahead, let u equal the exponent, so sine x. Take the derivative of that, you're going to get du equals cosine x dx. And from there, we can substitute in. So you get the integral of e to the u du. Matches up perfectly. Integrated, you get e to the u plus c. And then we just substitute back in. So e to the sine x plus c. And that's it for part 2 of 5.3.